So our first speaker is going to be Peter Vadasz. He is a professor of mechanical engineering right here at NCI-U. His background is deeply entrenched in physics, and I'm not really ashamed to say that he's probably more of a physicist than I am, even though I'm in the physics department. He's in mechanical engineering, but very strong physics background. So we're going to hear some about that today. So please turn your attention to Dr. Peter Vadasz.
Thank you. Thank you. Oh, there's a touch screen. Nice. Thank you very much. And I will start by saying that not only that I'm waiting for criticism as much as possible from this, but I invite a lot of criticism because this is really something that is new and is something that, okay, you are going to see. So it starts. Oh, it kind of goes not in phase with. So this presentation is heresy before observed, and but once observed, it collapses into science. So that's the pre-word to this. But the question is, why do we need a new theory of quantum mechanics? And the reason is we need a new theory of quantum mechanics because shut up and calculate, in my opinion, is not an adequate answer. And it also only shows the frustration that Richard Feynman had when he was not able to answer adequately students' questions. So what is that I'm going to present, and I'm going to go fast at the beginning of things that I think you are mostly familiar with, because this is, if I go at a regular pace, this is going to be very long. It's going to, I guess we have some 50 minutes in general, about 50 minutes. So I don't want to go beyond time. So what I'm going to present is a new deterministic quantum mechanics theory that is consistent with current mainstream probabilistic quantum mechanics. Then I'm going to be addressing the concerns arising from the current mainstream probabilistic quantum mechanics by using my proposed theory. There is only one postulate in the theories I'm presenting, and this is the electron, and actually most of, maybe all, subatomic particles are compressible fluids. So maybe I'm biased because this is my field, fluid mechanics, one of my fields, but you are going to see, decide by yourself at the end. I'm going to show the equivalence between the proposed deterministic quantum mechanics theory and the current mainstream probabilistic quantum theory. And at the end, I'm going to show, well, probably the last 20 minutes, I'll show you an analytical solution of the electron motion within the hydrogen atom via this deterministic quantum mechanics. So this is the first thing that I succeeded to solve. The rest is based on the properties of the equations and so on. Okay, so why it is important to introduce this new deterministic quantum mechanics theory? So let's see, there are a few reasons. One, the proposed deterministic theory is consistent with the current mainstream theory, which is probabilistic, and at the same time consistent with classical physics, that at the moment, the link between the two is not available. The proposed deterministic theory provides more detail than the mainstream quantum theory today. The proposed theory can predict the dynamics of transition between states, which the current mainstream theory, I'll show you why it cannot do. It doesn't predict. The proposed deterministic theory removes difficulties in visualizing the results using known classical and obvious interpretations. Then the deterministic theory proposed restores reality to atomic and subatomic phenomena. If you are familiar a little bit with quantum mechanics, you know a lot of people I say, well, that's reality is kind of missing here. The proposed theory unifies macro, meso, micro, atomic and subatomic scales. And the proposed theory is more predictive than descriptive, as distinct from the current mainstream statistical quantum theory. Then the proposed theory does not have a measurement problem. Its results can be presented with almost arbitrary accuracy, limited not by principles, but by accurate technology, but available technology. And last but not least, the proposed deterministic theory provides the only theoretical justification for the validity of the Schrödinger equation. Theoretical, because the Schrödinger equation gives results that have been experimentally confirmed, but there is no theoretical derivation for it. Now, I mentioned physical reality. What do I mean by physical reality? I'm not going to define what physical reality is. I'm going to give you two examples of what I call physical reality, and then we'll see how this is related. No two objects can operate the same region in space at the same time, nor parts of them can overlap the same region in space at the same time. This is one example of physical reality that I think is important. And you'll see that the existing quantum mechanics theory gives the results that show how two objects do overlap. The example that we'll see is the electron, and it will overlap with the nucleus as part of the solution. But we'll discuss about this. And I'll show you how this can happen. And no object can jump to space from one space location to another instantaneously and without passing the space in between these two locations. That's another thing there. Okay, so now I'll introduce you first the fundamentals, the fundamental concepts of the theory I'm presenting, and then I'll go on to show a solution for a specific problem. The history goes that it starts with Planck, that discovered his radiation formula, black body radiation curve, by practically fitting the theory that he had to the experimental data. And he had, in order to fit it, he had to assume that the energy levels are divided in quanta and are not continuous. Okay, so this is something that we know, we're familiar. Then came the Bohr model of the atom that introduced the planetary motion of the electron around the nucleus in the hydrogen atom, balancing the centripetal acceleration with the electrostatic force from the proton attracting the electron, and getting as a result he had to postulate, the first postulate he made is that the angular momentum is an integer value, an integer multiple of the Planck constant, of the reduced Planck constant, h over 2 pi. So this was the first postulate that he introduced and got the energy levels. As a result, the energy levels were fitting very well the spectral lines that were obtained experimentally. So he had very well success with this, but he had a problem because we know from the electromagnetism that any charged particle that is accelerated will emit radiation. Consequently, the result would be the expectation that the electron will spiral and collide into the nucleus, and this obviously does not happen. So this is inconsistent with the observed reality, and consequently, Bohr had to enforce a second postulate that the electron radiates only when it moves from one stable orbit to another stable orbit, but not when it moves in the same orbit, inconsistent with classical electrodynamics and mechanics. So this is the first time that he practically violated the principles from classical mechanics. The same was applied later in the theory of quantum mechanics that superseded the Bohr's model. So these jumps practically are still accepted today as they occur. So while Bohr model predicts correctly the energy levels of the orbital radii, it predicts an incorrect value for the ground state of the angular momentum. If you take the Schrödinger equation installed for the angular momentum, you'll end up with the angular momentum being equal to this value, which is 0, because L equals to 0 when N equals to 1, this is the ground state, and not L equals NH or L equals H with H bar when N equals to 1 is Bohr model postulate. So we have an angular momentum, which is 0. Now, angular momentum is defined here. Mass, velocity cross the radial direction, the radius or the distance, and zero angular momentum in the ground state as predicted could be, because of this, could be 1 or 2. Either the velocity is 0, which cannot happen in this case because turns out that kinetic energy is not. So velocity cannot be 0. Or the alternative is that V cross R, VDR is practically the same direction as R. So the cross vector, the cross product becomes 0, meaning that the electron moves radially and crosses through the nucleus, having then two objects occupying the same space at the same time, violating fundamental physics, principle of physical reality. So this is what one problem that then enforcing the postulate that the electron radiates only when it moves from one stable orbit to another stable orbit, but can never pass through the space in between these orbits during the sudden jumps, in order, he needed the sudden jumps in order to have the quantum. If you have a continuous transfer of movement to the space, there is no jump, there is no quantum. And he needed this because they suggest that we have quantum. So he postulated this, and the same was applied later in theory of in the what superseded the Bohr's model, I mean, Schrödinger equation and so on. The same quantum jumps in principle are accepted because there is nothing else to replace them. This is what happens in a quantum jump into two orbitals. Okay, so this is the Schrödinger equation that Schrödinger introduces. Here it is. He came back from the Alps from a winter break. He did some skiing there. I don't know what he did, ski or work on this, but he came out with this equation, and this equation practically is accepted up to until now as the mainstream quantum mechanics. It was amended by Dirac to include the phenomenon of spin that we'll speak later, but other than that, it's still accepted. By the way, if you introduce and use with Schrödinger equation the Pauli spinors, then you can still continue using it. Anyway, psi is some wave function, a complex variable, and the interpretation that Born gave to this psi was that this is the probability of finding the particle, or it's linked to the probability of finding the particle position. We'll see later exactly how the definition is. This V is a potential energy due to some externally imposed field. So this proton that attracts the electron, this is the potential energy is this of that field is this V. It could be this V, it could be any other. And M is the mass of the subatomic particle. If we represent the general, this complex function psi in this general form, then the psi times the complex conjugate gives you this rho, which is the probability density function, and the expectation of finding the electron at a position x will be then within the volume V naught will be given by this expression. This is the expectation. In this case, let's say in Cartesian coordinate, x will be x in the x direction, y in the y direction. In the z direction with ex, ey, and ez, with the head on top being the unit vectors in this direction. Okay, if we replace the definition that we introduced here, is just the wave function multiplied by its complex conjugate being just notation rho, it's obviously a real variable, then the expectation can be expressed in this form, which is useful for what we do later. And then there is some normalization that was introduced by Born, because the particle has to be somewhere, so the probability has to be 1 of finding the particle anywhere in the space. So that causes a normalization that is being used. And the following are the concerns that were raised from this theory of mainstream quantum mechanics. First, how can a particle in reality be also a wave? Because according to the Schrödinger equation, psi is a wave, but Born interpretation as defining the position of finding a particle, meaning that it's a particle. So how can a particle be a wave? That's the first question. Second question, how can the electron particle pass through the nucleus, meaning having two particles in the same place at the same time, as I've shown you that it occurs as a solution of this. The third problem, how can the electron jump suddenly from one stable orbital to another stable orbital without passing the spacing between these orbitals? And why does this jump occur at irregular time intervals? By the way it is explained by people that work in the field, they say, well, we are talking about probabilities. It's not that we speak about location. Well, it's probability of finding a particle, meaning that if you run the experiment several times, a lot of times, sometimes you find a particle here, sometimes here, and then you have the probability function. So we are talking about something real, running some experiments, getting some results of finding the particle in a particular place. So finding it overlapping with the nucleus doesn't make sense. But that's what the results. The other concern is, turns out, one of the things that turns out is that the electron has a spin. Now, spin, when you speak in mechanics about a rigid body, spin is an angular momentum around the center of mass of the particle. Now, how can a particle is a point-like thing. Can a particle, a rigid body, we can understand how to do it. How can a particle? So by the way, they tried to look what happens if the electron were a rigid body, and turned out that it cannot happen. The results were not consistent with the experiment. So it's not a rigid body. It cannot have a spin. So they say, again, that's quantum mechanics. There are weird things. Well, okay, but how this can happen? That a particle can have a spin. And then what happens is, I'll show you in a moment. What happens is, okay, you have the solution of the wave function, and this solution eventually, because it's a linear equation, you get the solutions, practically have infinite type of solutions. You have a superposition of solutions. That's a general solution. Yes, that's usually what happens when you have a solution to a linear equation. Well, when you run an experiment, you obtain only one value. And they say, well, that's what they call the wave function collapse. The wave function collapses from a superposition of modes to one single mode. And how can this happen? Either you have the solution and then the experiment confirms it, or if there's only one mode, why? How come now I'm asking in connection with what I'm going to present, the free electron fluid. Now this is a challenge not to the mainstream quantum mechanics, but to what I'm proposing. How come an electron fluid, because in my view, the electron is a fluid, that's the only postulate I'm stating, how does it not spread indefinitely in space? Because what happened is that Schrödinger didn't like the Born interpretation of the probability. He said it should be related, the wave function should be related somehow with the density, charge density of the electron. And it should be some wave and so on. And he said when the wave is localized, then you see it as a particle. And then the challenge was, well, but then according to your equation, if you solve it, this particle spreads. It doesn't remain localized. Well, the electron experiments, it may remain localized. So this was a challenge which Schrödinger didn't have an answer to. I'm going to show you what the answer is, according to me, because the same challenge can be made to the electron field time proposal. Why doesn't it spread indefinitely? Okay, first we'll start by introducing. Okay, so I'm saying the only The only one possibility I'm introducing the electron, most likely all subatomic particles in reality are compressible fluid. They possess a mass density rho, which is a variable, changes with space and time. And if they are charged particles like the electron, then they possess an electric charge and density, which is rho e of x. And then I can define the center of mass of the electron fluid, which is the definition of center of mass from rigid bodies, from mechanics of rigid bodies. But hey, this is exactly the same as the expectation of finding the particle from the Schrödinger equation. Exactly the same definition. So the center of mass of my fluid is the same as the expectation value from the Schrödinger equation. And we have that equation that emerged from defining the sum of all particles as compressible fluid, identical to the equation that emerged from the equation and for interpretation. I can show here, I mean, the next slide is showing practically the same thing, but for the normalized expectation. So I'm going to go and fast with this. Now that the mass of the center of mass of the electron fluid was defined, it becomes appealing to define the center of mass of the electron fluid as the electron particle. So now we have the electron fluid, which provides the wave, and the center of mass of it, which is the particle. That's my definition, my interpretation of the center of the particle. So that's how I'm going to call electron particle will be center of mass of the electron fluid. And with this interpretation, it becomes clear how two particles can be at the same place at the same time, in the same region of space at the same time, without having any part of the matter or the physical objects even contacting each other. This is just the same as a small sphere concentrically located in the middle of a torus. This is a torus, and this is a sphere. And I can place the sphere in the middle of the torus. They share the same center of mass, but they don't even touch each other. The matter doesn't, the object don't even touch each other. Okay, so that's the distinction between the electron fluid and electron particle, or the center of mass of the electron fluid. Okay. So this is what I already mentioned. Okay, one additional thing I want to mention, that once we make this definition, we have to understand that it's distinct from solid mechanics, where we practically have 6 degrees of freedom. We have practically 3 degrees of freedom of linear motion, the x, y, and z direction, and the 3 rotations in the 3 rotating directions. In the case of electron fluid, we have a 9 degrees of freedom because we can have contraction and expansion in each direction, in addition to motion, linear motion and rotation. So we have 9 degrees of freedom practically, so it's a bit more elaborate to deal with. So what are the governing equations that will govern this electron fluid that I just defined? We have the Navier-Stokes equation for fluid dynamics and the Maxwell equation from electromagnetism. The electric current density, which is this vector JE, is nothing else but the electric charge density multiplied by local velocity of the electron fluid. So that V, which is a function of space and time, is the electron fluid velocity, and rho is the electric charge density. With this, the Navier-Stokes equation are the mass conservation of equation of mass continuity, and the linear momentum conservation, which is called momentum equation. Now, what you will see here on the right-hand side are typically the forces. On the left-hand side is mass times acceleration, is mass per unit volume times acceleration. Minus gradient of pressure. Now, what happened is that my claim here is I did not include shear stresses in the stress tensor because I have no evidence that there is any shear appearing at the subatomic level. Shear usually includes dissipation, and I'm not familiar with anything that dissipates in the motion of the electron, for example, or something like this. Maybe it does, but at the scale it's so small that so the shift, the stress tensor is practically only on the diagonal. You have the elements of the pressure. So we have only the pressure gradient here. And the other forces are this is the force that is applied by the proton on the electron fluid. And this is the intrinsic electrostatic field. The EE is the intrinsic electrostatic field due to forces that differential electron fluid elements impress on each other. What does it mean? If we have two negative charges, they will repel each other. Now think about it. Now the electric charges are now spread around continuously, so they repel each other at every single point. And this is the field that does that. It's actually the repulsion. This is an unknown variable that will change depending on how the density charge is going to be distributed. So these are, and this is practically the magnetic effect due to the V cross V being the magnetic flux density, and these two together are the Lorentz. These three together are the Lorentz force, if you want. The next one is the conservation of electric charge. So this is the equation of electric charge conservation. Then we have the Maxwell equation, Coulomb law in field form. I separated the field, the electric field of the electron from the electric field of the proton, because the electric field of a proton can be solved given that we have the proton density uniformly distributed within the nucleus and is zero outside the nucleus. So we can solve for this. We know this is the Coulomb law for the coming from the proton, and then the Ampere law, the Faraday law of induction, and the Gauss law of magnetic field. These are the Maxwell equations. The only thing that will be different, what you are familiar with, is instead of capital J, which is the current density, you are going to see the rho EV, which is probably the same. Just I want to express everything in terms of velocity because the Navier-Stokes equations have the velocity in them. Okay. Here I'm making the first assumption. I'm assuming that the mass density divided by the charge density, or the absolute value of the charge density, equals to the same value as the mass of the electron divided by the charge of the electron. So this is an assumption, implying that, and this is a constant ratio between the electron mass and electron charge. The reason for that is that I cannot see an electron charge moving without a mass that is in it. Yes? Okay, so I agree that this can be expanded and the relation will be relaxed. I know that. At the first instance, I'm assuming that this relationship exists. So this is the first assumption. The second assumption is a constitutive relationship between mass density and pressure, which for known material at macroscopic level, we have experiments and we know the values, we can evaluate them. For the electron fluid, I don't know. So I'm assuming a linear relationship between density and pressure, with this beta P being the compression coefficient. And have a look, this compression coefficient 1 over rho naught over d rho dp. And this is interesting because dp rho, square root of dp rho, is in compressible fluid dynamics, this is defined as speed of propagation of a wave. So I call this V naught, square root of dp rho, the speed of propagation of the electron fluid pressure wave, in analogy with compressible fluid, assuming isotropic wave propagation is customary in compressible fluid dynamics. Okay, now let's see the equivalence between the electron fluid Navier-Stokes equations and Schrödinger equation. This is the Schrödinger equation. Again, I'm expressing the wave function as R e to the power is over h. R and s are scalar functions of space and time. And if I define rho as r squared, or the product between the wave function and complex conjugate, then and I define mv as gradient of this s, I get the v. Then I substitute this into the Schrödinger equation. You will get this set of equations that was obtained by Madelung in 1926 with, this is the same potential energy that we have here in the Schrödinger equation. This was called the quantum potential, and Schrödinger attempted to link this quantum potential to, that's the definition of quantum potential that comes from the derivation, and Madelung attempted to link this potential energy or the quantum potential to the pressure gradient in the Navier-Stokes equation or Stokes equation, and he didn't. He was not. Yes.
Sorry, I just had a question. So, when thinking of electron as a fluid, are you having to rewrite all those established equations of electromagnetism and fluid mechanics and all of them?
When we realized it's the same equations, I didn't
Same
change.
exact equation, you don't have to.
I didn't. The only thing that changed, I think, was the forces on the right hand side that are relevant to the electromagnetic effect. That's it. But it's the same equations. Didn't change anything. Anyway, so he attempted to do that. He didn't succeed to link this to the pressure gradient. So what I'm doing is I'm taking the electric field, the electron electric field, and defining it and linking it to this quantum potential. And then this will appear as this term in the equation, replacing this with EE. And then I still need to see what this potential energy is. And here, to do that, I'm splitting this V into two parts. One is due to the proton attraction, or the potential energy of the proton electric field, and the other one is linked to the pressure gradient. So there is a second potential energy, or potential V2 over M, that if you define it like this, you get eventually this term in terms of the wave function is practically the rho, which is the psi times complex conjugate of psi. When we introduce this as the two potential energies into the Schrödinger equation, we get an amended Schrödinger equation. We have an additional term in the Schrödinger equation, which is nonlinear. So if we convert this, at least this term, into dimensionless form, we have as a result the Mach number, electron fluid Mach number that emerged as a dimensionless group, which is defined as some characteristic velocity of the fluid motion, electron fluid motion over this V naught, which was the speed of propagation of the electron fluid wave, and this is an additional parameter. This is obviously non-existent in the present quantum mechanics, and this explains, for example, why, in my view, the existing results of quantum mechanics fit so well to experiments. If Mach number is very large, then obviously the situation is very correct, very accurate. So for very large Mach numbers, it will give very good results. So this is the dimensionless form of the same equation. I'm just showing in general form one can replace this potential energy with any potential energy. So that's the amended form of the Schrödinger equation. That in the special case of very large Mach numbers is identical to the Schrödinger equation. Okay, so the solution to the Schrödinger equation is the original Schrödinger equation, not the amended one, is a superposition of infinite mode, but upon observation or measurement, it turns out that the wave function collapses to one single mode. So the question is, if we found the particle at some point C, where was the particle just an infinitesimally small time before the measurement? And yes.
We have a nonlinear.
No, that's what I'm saying. The original Schrödinger equation was that's the point I'm coming. So the original equation has this superposition, it collapses to one single mode. You already see where I'm going. And when you ask where was the particle the moment before it was measured, there are three answers. The naive realist position, Einstein, Podolsky, Rosen, and others said the particle was at C. The quantum mechanics orthodox position is the particle was nowhere until observed. Only the measurement produced the particle and forced it to take a stand. And then there was the agnostic position that refused to answer. These were the three positions that were. often. And now, obviously, today, this is the position that everyone, well, at least people that know the experimental results, at least the ones that are now proven after the experiments of Bell theorem and so on, this is the position that everyone is taking. Very few still believe on the first one. So this equation is nonlinear. Obviously, you can't do the superposition of individual eigenfunction function. The wave function collapses naturally due to nonlinearity. Okay, only one mode. By the way, the same thing happened in natural convection. If you take natural convection phenomena, you have the solution with infinite modes. Only one mode survives there, and there is a reason that the solution shows, but it's not. I'm not going to expand. Anyway, I'm combining the equations and eventually lead to this type of equation, and this combining a few of the equations I spoke before, we end up with this type of equation, which obviously is a wave equation, is of a hyperbolic type. And from compressible fluid mechanics, we know that this equation can have shock waves at certain Mach numbers. Shock waves means that this particular occurs when the equation is excited by a source term at the right-hand side of the equation, but these are accurate description of quantum jumps, meaning sudden transition from one stable orbital to another stable orbital. All properties suddenly change. So the particle or the electron fluid does not jump without passing through the space in between. Which, hold on, Bohr and whatever never followed, they said, yeah, it cannot pass in between because then the quantum is destroyed. The quantum is not destroyed by having it pass through between in a short run. Actually, just 3 years ago, there is a long group led by this guy, Minev, that published in Nature a paper showing beautiful results, catching and reversing a quantum jump mid-flight. And they practically show, and they conclude, the experimental result demonstrate that the evolution of each completed jump is continuous, coherent, and deterministic over a short time scale, while it can be unpredictable and discrete over a long time scale. So we are talking here about just the same as we have for compressible flow mathematical hyperbolic type with shock wave. So this is the explanation of the shock waves. Now let's go to the spin. Now that we know that we don't have anymore a spin of a single object, a single particle, but of a fluid around the center of mass, this is like we have in macroscopic terms the spin of, let's say, a tornado. That's exactly, you see the spin and you see how it moves. It spins, it moves. Actually, the next one is even better. It shows, you see how it moves, the center of mass moves, but it also spins. So you can have an orbital motion and you can have a spin at the same time. That's in fluid dynamics. Okay. Now, if you want more proof that the two effects are very similar, a spin that occurs in a tornado is due to Coriolis acceleration that if we move to the right-hand side of the equation, looks like this. The electron fluid has this term in the equation, B cross B. You see the similarity between the two, and also the spin occurs due to magnetic effects. So magnetic effects analogous to rotation will provide you the same effect, and that's the reason for the spin. Now let's speak about the entanglement, because this is really the talk and hot topic of that. So what you do an experiment in one place to get a result, and instantaneously, miles away, you do the experiment, it changes the result according to what you get here. So that's what Einstein called spooky action at a distance that cannot happen. The signal moves at the speed higher than the speed of light, cannot happen. It violates this postulate on theory of relativity, which was proven. So there have been Bell-type experiments that prove the violation of Bell's inequality, implying the local hidden variable that were introduced by the EPR paper do not exist. The proposed deterministic quantum mechanics theory here is not local, although the equations are local in the following sense. The equations produce solutions that are local. The values of the dependent variables, the local velocity, local mass density, and so on. But from this, we can evaluate the local linear momentum and then the local angular momentum and the local energy. And the next step, we have to average them over local properties to get global properties that can be associated with the center of mass. And that's what the existing quantum mechanics directly is looking at, what happened to the center of mass. So when we average this angular momentum, local linear momentum, angular momentum, and kinetic energies, you get this global variables. Okay, let's show you an example. First, an example of the center of mass itself is a global property. You change the density, and it changes instantaneously. If you change the density any particular location, very far away, you can change the rho very far away, and the center of mass changes instantaneously because of the definition. So here, you want to call it spooky action at a distance, fine, but it's the definition that causes it. Let's take the angular momentum. The local angular momentum, and I calculated it. Oh, I have to go fast because I want to get a solution. So the local angular momentum that is calculated is by using this equation. And this will be a local value. But then we average it over the volume. In this case, I'm averaging of the volume of the electron fluid. And getting a global value that doesn't depend anymore on space. And changing the local value will immediately affect instantaneously the angular momentum, the global value. So let's think about the local angular momentum of two electrons. There's the one, and there's the second, A and B, and evaluate their total angular momentum, LB and LA and LB. Then for an entangled pair of electrons, this will be the total angular momentum. And then we can substitute for practically adding the volume of A plus the volume of B in an entangled pair. And then you see that the total angular momentum equals to the sum of the total angular momentum of each one of the electrons, just by adding the integration of the volumes. And well, we know that the total angular momentum is constant because of conservation of angular momentum. So the angular momentum, total angular momentum with B, of electron B, equals to this constant minus the constant angular mass of the angular momentum at A. So let's say that if initially A was spin up and B was spin down, the total angular momentum was 0, and then changing the value of LA to spin down causes immediately LB to become spin up just because of conservation of angular momentum. L is constant. So this is just instantaneous relationship that don't have to transport information. It's just the way we define it that makes it like this. So what we measure when we measure spin is not something local, but something global, measured local. Example, hydrostatic pressure of a fluid. We measure it at the bottom, but it represents everything that happens above it. Okay, that's just to give you an example that you can measure a global value, global property local. In the case of hydrostatic pressure, it's not instantaneously transported. It takes the speed of sound. It's at the speed of sound that it transports. But still, it's an example that shows that you can measure a global property locally. And that's the idea that I wanted to make. And that's what I think spin that is measured is yes.
But I think entanglement is more than that. It's more than that. You're just talking about correlations. It's much deeper than it's that the real essence of the camera comes with incompatible observations. that are
Okay,
not
so you are talking about caution Specker theorem?
talking about like the Bell inequality violation.
Yes, but Bell inequality is exactly that. So the correlation, Bell inequality, the original one is actually exactly that. Then it was eventually developed. And then caution Specker theorem came and say you practically, what it says is the measurement at B will be affected on what you decide to measure on A. That's what you mean? Okay. Well, if you decide to measure on A, not spin, but something else, it wouldn't affect B.
That's not what observations show.
Oh, no. If you measure something else, that's exactly proving it. Yeah, okay. Okay, so I have practically about 7 minutes to finish. So I'm going to go fast through the solution. So the basic equations that I should solve. First of all, I solved the equation of the electron motion in the hydrogen atom, simplified to 2 dimensions. So I'm taking the azimuthal direction, the radial direction, assuming we have some average over the polar direction. Okay, that's for simplicity. I'm going to expand it 3 dimensions. Don't think it's going to change much on the major results. And turns out there is a basic equilibrium stationary solution to this set of equation, meaning that there is no velocity stationary, and the electric field of the electron, the density and the charge density are a function of radius only. And if you assume this and you solve the equations, I'm going to go fast with the solution. I'll show you straight the solution. You end up with, okay, you end up with a solution. I should have, sorry, let me show you. Yeah, so it gives you this solution for the electron field, for the electric field. And then if you substitute and this looks like this, there's the electric field solution. If you substitute this into the other equation for the electric charge density and eventually convert it to the mass density, for the mass density, you get this shape, which is exactly the same shape, although not exactly the same solution, very similar, but not the same as the solution to the Schrödinger equation for rho. Then I converted all the equation dimensionless form. So what you see here is the star are the dimensionless variables. And here we have all the equations written in dimensionless form. And now you have the Mach number showing up in the equation because of that. And perform a linear stability analysis of the basic solution, introducing perturbations that are small. So we can linearize the equations. And these are the linear equations that, and again, I'm going to skip it, separation of variables. In the time domain, we have this equation. This is the solution. You have here the case of this guy, the separation constant being negative, in which case you get this complex conjugate solutions. And when it's positive, you get this type of solution. Obviously, this solution leads to instability of the basic solution because this thing explodes in time. It grows indefinitely. So this seems the basic solution is unstable when chi is positive and is neutrally stable with oscillations because these are oscillations in time if chi is negative. Then again, we have the azimuthal solution that gives practically the same eigenvalues as the Schrödinger equation. That's practically what you get eventually. And again, I'm going fast with this. In the radial direction, again, we get an equation that is very nasty, but again, manageable. And these are the velocities that are being obtained, which are standing waves. Actually, if the initial velocity is 0, this is how they look like. I have here an example of type of waves. Again, this is good for demonstration to students. you are most likely familiar with this type of right, pure right traveling wave when, which is this, and then pure left traveling wave when the coefficients here are equal in this form. And then we have standing waves, which is the wave, the red wave, which is a superposition of the black wave moving purely right and the blue one moving purely left. And then obviously you can have a more general form of a wave pack, which looks like this. Anyway, coming back to the equations. Okay, so we have this, and then we substitute this and evaluate the fields, the electric fields. In this case, for m different than 0, m equal to 0 gives the orbital motion. That's, again, I'm not going to go through the details because we don't have time. I have to finish fast. So, okay. So once I solve the equations, I can evaluate the linear momentum and then integrate it to get, so this is the local linear momentum, and then integrate it to get the total linear momentum. And then I can go and evaluate the angular momentum, local angular momentum, integrate it to get the total angular momentum, get the solutions that I've got, and evaluate for each value of m. So evaluating with m different than 0 gives me that the angular momentum is 0. It vanishes. When m equals to 0, it gives this solution. That's the solution to m equals to 0. But if you now integrate over a period, then again it becomes, angular momentum becomes 0. Now, why is this important? Is because for all these values, it turns out the kinetic energy is not 0. Exactly as we had from the existing quantum mechanics theory. So here I evaluate the the kinetic energy for m equals to 0, and for m different than 0 for different values of m, I get different values for kinetic energy. In each case, this integral can be shown to be non-zero. So now evaluate the center of mass, because what happened is that now I want to see the motion of the center of mass. So I'm going to evaluate the center of mass using the same solutions, and turns out the center of mass is given by this. For all m's actually end up to be, Rn is the dimensionless form of the radius of the nucleus, which is very small, much smaller than 1. So we can have this as half. 1/2 is quite a good approximation. And then in order to see the motion of the center of mass, I need to convert it to Cartesian coordinates, because you'll see in a moment why. So converting this center of mass that we receive into Cartesian coordinates introduce the azimuthal angle phi, and then taking the integration accordingly, you end up with a solution that looks like this. YCM is 0 and XCM is this. Now this shows a variation of the motion of the center of mass in the x direction, radially, horizontally, with no y component. And in some cases, when m equals to 0, the center of mass is at the nucleus. Our center of mass can be at the nucleus as the fluid practically moves around it, not a problem. It's not an object. This is the motion that you are going to see of the center of mass. Actually, I have a simulation here that will give you, if you look here, this is the center of mass, and this is the electron fluid, and this is an annulus, practically its density plot. The darker it is, the more concentrated the electric charges of the electric mass is there. So have a look how the colors are changing, and the center of mass is moving through the nucleus, getting closer, getting here, and here starts moving in the opposite direction. As the electron charges, electron mass or electron charge move around. Now, I didn't include this here, the radial component, to have made it less clear. So there is a radial variation too, but I want to show just this azimuthal change with the motion of the center of mass. Okay. I'm going to skip this. Oh, so what happened is that we got this value that is practically 1/2 for the radius center of mass. And if I'm assuming that this is wherever the center of mass is actually where the Bohr radius is, that we know, and practically introduce this, I'm getting practically that this R infinity is 2 times. So the center of mass is R infinity over 2, and this is related to the Bohr radius. I'm getting this relationship between Bohr radius being at half a location from rho R infinity, which is the boundary of my domain, which I didn't discuss it, but it's an important point of it. Anyway, now evaluating the total energy or binding energy of the electron gives me this result, that if I continue with this and getting this, and if this will come out from the weak nonlinear analysis to become -1, I'm getting practically the familiar energy levels that we are familiar from the either Bohr atom or the Schrödinger equation. So it's exactly the same. The solution in the radial direction is spherical Bessel function. Now I'm going to go back to the bottom line, to the final slide straight. The solution is practically using Galerkin technique to evaluate it, and turns out that there is a stability map for the solution that looks like this. Depending on the Mach number, these are the values of chi equals 0. This is where chi is less than 0, so we have neutrally stable with oscillations, and here we have unstable solutions. And this is for the final result of the linear stability analysis. The next step, which I'm working on now, is weak nonlinear analysis that will give me the amplitudes of the motion, which I don't have yet, the frequencies, exactly the frequencies of the motion that I don't have yet, and will produce. So it will try to complete the whole picture and give me the closure to the whole thing. And with this, I'm going to straight the conclusions. Okay, I'm going to get first to the conclusions. Show that the conceptual framework that I introduced, I show it is consistent with the mainstream statistical quantum theory. And since the governing equations were derived from first constant principle, the proposed theory is also consistent with classical physics, causality, physical reality, determinism were resolved, and I've shown you simple explanations of the concerns that were about the existing theory. The meaning of the particle wave duality is clear also, and the possibility of a particle like the electron to cross through the nucleus, because it's not an object, was shown. The Ponstein particle can have an intrinsic spin, and the quantum jumps are frankly not more than shock waves, and the natural colossal wave function was shown to be part of the solution. The solution, okay, so the fact that we found sometimes the center of mass in the same place as the nucleus was seen by objection by Einstein, for example, and even observed by Bohm. I showed you that this is perfectly consistent with what we are talking, what I proposed, and the linear, so the linear stability showed you solutions of the problem. Also, you see how the Schrödinger equation came out directly. Any questions? Yes.
Two questions. Can you explain charge and spin quantization?
Charges?
Can you explain charge quantization and spin quantization?
Okay, so spin quantization, in my view, is going to come out as a solution the same way the velocity comes out quantized, because of the eigenvalues. You get one eigenvalue, that's it. You get a lot of eigenvalues, but one of them is going to be selected, okay? Because the same way as in natural convection. And the same for charge density. So if charge density is quantized because all the equation is going to give you eigenvalues, eigenvectors, if you have an infinite domain, you don't have the separable variables will give you the integral, not the sum. So it's not quantized. Okay, so that's the distinction. Every single variable will be quantized, and the only reason that it remains such, and it's not superposition because the problem is non-linear. And although we do have approximations that we do with linear analysis and so on, because these approximations have to gradually be consistent with the nonlinear equations, you cannot have this superposition. So that's the reason that it, but they will come out naturally from the solution of the equation. The same way that rho comes out naturally here, rho E comes out naturally as a quantum, not as a continuous. Yeah, the second question?
Oh, it was spin.
Okay. Oh, the spin, the same reason. For the same reason. Yes.
I was wondering how you would, if you're getting, say, the same results as we're seeing using the theory that already exists, how would you propose going about sort of proving that your method of doing it is correct versus what we already have in place?
Okay, so what we have in place is very good. It works. Actually, the claim that Einstein had that this is incomplete was proven wrong. 2015, I think, was the last experiment to close all the loopholes on the Bell's theorem experiment. So there is no problem about it. The problem that it still has, and that's why I showed the importance, the first thing I showed the importance of what I'm presenting, is that it's vague. It's vague. You can't explain these things that physically you want to know. How come you have a particle that has a spin? Or how come you have two objects in the same place? Here you have the explanation. So it merges now and shows a clear connection between reality, physical reality at the macro level, with the exactly the same happening at the low level. It fits. That's the only thing that is doing, and it's giving much more detail. So now you have much more detail. You can, for example, think of measuring pressure, which nobody thought to do under the existing quantum mechanics because there was no pressure there. Current equation, there's two things that are missing: magnetic effects and pressure. And this, by the way, I didn't go through it, but that's exactly the reason that the electron field doesn't spread indefinitely. Because pressure, you saw that there is an equilibrium solution, stationary with oscillations, but you have an equilibrium solution. Second, you have magnetic effects. Now, think about the charge, start moving. What is doing? Getting the magnetic field. The magnetic field, what is doing? Then slow, getting an opposite effect, causing you to move in the opposite direction. Okay, so it's canceling the original effect. So both magnetic effects as well as pressure are reasons for the wave function not to spread indefinitely, for my electron field not spread indefinitely. And these two effects were non-existent in the linear Schrödinger equation. That's why you couldn't answer the question, how come your equation spreads? If you want to have it. Yes.
It seems like the math was flying by pretty fast. What you're saying is that there are continuous solutions, but the continuous solutions are so unstable that they can't really be measured. Or if there was some way to get into that kind of measure the medicine.
Okay. So it's not a continuity here, the quantum is not a continuity. When you have eigenvalues and eigenvectors, eigenfunctions, it's continuous, but is a superposition of a few continuous functions or infinite continuous functions. By the way, you can have a superposition of a finite number of functions, which is fine. What you cannot have is an infinite number that starts converting the solution. If you have infinite number of modes, making the superposition the sum of all the modes, as you do with the linear equation. But it's still a function of x, y, and z. But it's the eigenvalue of that, which is the eigenfunction of that, which makes it quantum. And then, if you take only this eigenvalue and integrate it over the whole volume, it's not a function of space anymore. But this is still quantized because you pick up only one mode. If you pick another one, you get this different integral. So this integral is going to be a function of which mode did you pick. Okay, so you can call it L of K. It's not just okay. That's where quantization comes into effect. You cannot have a continuous values of energy. You have only certain values. I mean, energy cannot change. Doesn't mean it doesn't change in space.
Impression that it was unstable in between there.
It is. It will not stay there. No, it will. Yeah, it will jump from one to another because we have this equilibrium states that
But it,
has to go between. The experiment showed that. Just 3 years ago, the experiment came up in between. So it will go in between, but it will jump. So it's so fast that you don't see it. So this the issue of shock waves is also an interesting effect in fluid dynamics. It's much more understood there because what we do there is take a boundary layer around the shock wave. The problem is that when you make a shock wave, when you go to a shock wave, it's not as entropic anymore. It's irreversible, so it's not how difficult to analyze. But it has been done in fluid dynamics. It's a difficult topic to research, but it has been done. Yes.
So, in comparison to classical quantum mechanics or just in general, are there any limitations to your quantum model or
Limitations on measurements?
in terms of like modeling?
I don't think so, but I didn't prove it yet. All I proved it so far, what I showed so far, is a specific example for the electron in the hydrogen atom, and there is still a road in front of me to show additional things, but that's about it.
What about quantum electric dynamics?
Well, I have them actually questions here. Okay, I know what you mean. Obviously, we need to go there. The next step is to go there, and hopefully, I hope to find the fine structure and so on. But yeah, at the moment, the quantum dynamics we can treat this that have them.
No, but they're well understood.
Yes, but you have all this normalization that the group that a lot of people are not comfortable with.
I think it's pretty well understood now.
Okay.
Yeah.
Yes.
Just to follow up on my feedback.
So I wanted to immediately after that, I want to take a minute. Because on this issue, I do think is the one that probably might introduce the moment. Because if the electric charge and if the center of mass and center of charge are not at the same point, then you have a moment. And this can introduce the spin from a different direction. So that's one of the things that I wanted to speak with you after that. If you don't mind, stay 1 minute. Thank you.
Any other questions for our speaker? All right, let's thank you.
Can you